Hello, everyone. My name is Dulguun, and me, Dylan, and Alli have done a project on determining the technical feasibility, specifically on land area, for a novel solution to create emissions-free heating for industrial production called solar thermal trapping. It uses the greenhouse gas effect for good. We chose this project because climate change is one of the biggest challenges of our generation. It will impact our ability to live on this planet unless we generate truly different technological solutions. While it likely won't directly cause our extinction, it causes instability that increases risk of other existential threats, such as pandemics or AI. And even if it does not lead to extinction, it is highly certain to cause massive harm, millions of deaths, and trillions in damages. Billions are highly vulnerable, with half the world already experiencing severe water scarcity for some part of the year. Using the ITN framework, industrial production is important because it is third in global greenhouse gas emissions by sector, after electricity and transport. It contributes 24% of global emissions, and this is only projected to grow and become the biggest emissions contributor in 6 years. This is tractable because there is potential to reduce 40% of industrial emissions. Yet it is also hugely neglected, receiving less than 1% of all climate change mitigation funding.
Given the potential to reduce industrial production's climate impact, we focused on a novel solution called solar thermal trapping. This solution has potential to create emissions-free heating, but has not yet been implemented in large scale. So, how does solar thermal trapping work? First, solar radiation is concentrated with mirrors and directed to the central receiver. Second, the receiver uses thermal trapping to retain the heat. Like the greenhouse gas effect, solar rays can enter, but heat cannot escape. Third, the heat from the receiver is transferred to a heat transfer fluid, helium, which will then flow in underground piping to an industrial reactor. Finally, once the heat transfer fluid in the reactor has cooled, it will be piped back to be heated by the receiver again so that its heat is recycled. The point is, high temperature generated in the receiver through thermal trapping can be directly used in manufacturing, instead of burning fossil fuels to heat up materials. To reduce industrial heating's emissions through large-scale solar thermal trapping, we need more research, development, and funding. First, we must assess the feasibility of scaling this technology, as current research has only produced thermal trapping experimentally in small scale. So far, researchers have shown economic, environmental, and technological feasibility at temperatures above 1,000 degrees Celsius. However, there's a gap in research concerning land area requirements. If we can determine land area feasibility, more research and development funding will flow to this solution, enabling large-scale implementation and an eventual reduction in emissions. The core of our project focused on calculating the land area that is needed for a large-scale implementation of solar thermal trapping. We created a mathematical model to determine the land area needed to use concentrated solar thermal trapping for various industrial heating processes. We started with the industrial process, how much power one reactor uses. Then we calculated the heat loss during piping of the HTF to figure out the heat the receivers need to supply. Next, we used the efficiencies of the receivers and collectors to figure out how much solar radiation we need. Finally, the average solar radiation a location receives was used to get the amount of land needed for one reactor.
Next, we determined the percentage of existing steel and cement plants that have enough land area to implement this technology. We chose to look at 27 cement and 10 steel plants in the western US due to its high solar insolation throughout the year and availability of climate change mitigation funding. For each cement plant, we found the area of flat, undeveloped land within 5 kilometers of it and the average insolation of the location. We found the average pipe length to the solar concentrator field. Then, we used our mathematical model to calculate the required area, and we compared it with the available area. Here are our results. We found that out of the 27 cement plants and 10 steel plants considered, 19 cement and 5 steel plants have sufficient land area nearby to support solar thermal trapping. All plants that do not have available area are either in urban cities or mountainous areas. Also, using our mathematical model, we calculated the land area requirements of common manufacturing processes, assuming a typical pipe length and average direct solar irradiation. To wrap up, in this project, we determined the technical feasibility of a novel solution to create emissions-free heating for industrial production called solar thermal trapping. We showed how solar thermal trapping uses the greenhouse gas effect for good and determined most plants do have enough land available. What are the next steps for our project? First, our land use results are approximations and need to be optimized for minimal land area. We need to verify our mathematical model with computer simulations. Lastly, during our project, we noticed that the technical implementation of the process itself has gaps. We need to design higher temperature insulation for piping, as current piping insulation only works for lower temperatures. Our current solution also only works during the day, so we need to implement a secondary power source when the sun is not out. Our project aligns with our long-term goals because we all love math and analyzing data. As non-trivial fellows, we are all passionate about having a positive impact, and we're also all looking to work on climate change in the future. So this concludes our presentation, and thank you for listening.